Can you hear me?
Yes, we can hear you. We can see your slides.
Okay,
Start now.
perfect.
Thank you.
Good. Yeah, hello. Thank you so much for the opportunity to present remotely. My name is Tom. I'm currently a PhD student at the Max Planck Institute for Intelligent Systems in Tübingen. And yeah, I'm presenting our paper on challenging the validity of personality tests for large language models. I will give a short motivational introduction and a very brief introduction to measurement theory before I present the results of our paper. So the latent properties that we were interested in before the large language model era was relatively sparse. Usually we cared about performance. Fairness is definitely one extension, but we didn't ask ourselves about the personality of a convolutional neural network or the IQ of some classifier. With the growing capability of large language models and vision language models, this somehow changed from two sides. So on the one hand, the benchmarks grew more and more like human exams. For example, MMAU could be like a very long multiple choice question task that you could also ask like graduate students or something. On the other hand, I hope you can see it a little bit on the right side of the slide. In the GPT-4 technical report, there's a whole battery of human educational exams that were applied to GPT-4 to evaluate it. And on top of that, people also started to apply psychological tests to especially to large language models. For example, a test for a theory of mind, which is a psychological field that investigates how well humans can understand the state of mind of other people, but also, of course, personality or tests for psychopathy. And then what oftentimes happens in these papers here is, I want to emphasize, it's just an example. It's not about this particular paper, but what oftentimes happens is that people then compare the mean or maybe the standard deviation of the scores of these tests. So you would score, for example, in this case, the answers of GPT-3 to a personality inventory, and then compare this mean score, here in this case 3.5 on openness, to the human average openness score. And in our paper, we asked the question, is this okay? Can we do that and interpret these as personality scores of GPT-3, for example? Is this, in other words, just another benchmark? And how would psychologists test this, evaluate this, and see if this measurement instrument really works for large language models? So because personality constructs are so abstract, I chose a different example of a measurement device for a brief introduction into how psychologists do this. This is an oximeter, I think, is it called. Please, if there are any specialists on these devices in the audience, please give me a chance. It's just an example. I'm not an expert on this. But what this does is it measures your heart rate and blood oxygen level. And you put this little thing on your finger, and there's a little lamp in this fingertip thing. And what people have figured out is that your heart rate and your blood oxygen level produces variance in these two light signals. So we can basically write the light signals or the light scores as a function of the true latent, in this case, pulse or oxygen level. So yeah, to introduce a little bit of vocabulary here. So we call this score, this infrared light score in this example, the manifest variable. Then there's usually a mean value or a bias, and then the loading of the latent variable oxygen in the example, or heart rate, and a measurement error or noise term. Now, what somewhat happens is that we take this measurement device that was specifically developed for one population, namely humans, and apply it to a completely different population of subjects. Here I created this image of a robot, but of course for personality tests, we applied this personality test that were developed for humans to large language models. And now, assuming that we don't know about the inner workings of the robot, and if the robot has heart rate and oxygen level, how would we figure out if this measurement device actually measures the same thing? And what psychologists do is something called measurement invariance investigation. So what they basically do is that they estimate the parameters of this equation and yeah, compare them to the parameters of the human equation. There are weaker forms of it. The weakest form is the so-called configural invariance, where basically only the structure is of the equation is equal. So the robot might have oxygen and heart rate, but none of the parameters, so the bias, the loading, or the noise term, are the same as in humans. Then there's weak invariance, which is structures equal plus the loading, the lambda term in this equation is equal. And then the strongest form of measurement invariance is strong measurement invariance, where also the bias and the noise term between the two populations are equal. Now, coming back to the application of tests to LLMs, that means that if we see equal scores in humans and LLMs, for example, for personality questionnaires, that means that if these parameters are not the same, we cannot interpret these scores equally. In other words, only if we have strong measurement invariance, we can actually interpret this score for GPT-3 in this case as the same thing as human personality scores. So now to the results of our paper. The first thing that also psychologists would probably do is so-called exploratory factor analysis. That can be factor analysis, could also be PCA. And what you do is you look at the scores of, in our case, of the Big Five inventory, a very common personality test, which models personality as a 5-dimensional construct with 12 items or 12 questions each for each personality dimension. And 6 of these questions are so-called false key items, and 6 of them are true key items. Just to give you an example and some intuition, and a true key item would be when I ask, are you a person who is outgoing and sociable? And I answer, yes, I agree. Then my agreeing to this question would correlate positively with the latent variable extroversion. So the more I agree, the more extroverted I am. And false key would be exactly the other way around. So if I ask, are you shy and introverted? And I agree, then this would negatively correlate with my true extroversion with the latent variable. So now we can do PCA. When we collect these answers, we can do PCA. In this case here for 2 human samples. And then you see on the left, the, I think you should see my mouse. You see on the left the items here, E for extroversion, A for agreeableness, etc. And then plus for the true key items and minus for the negative keyed items, false key items. And you see that each question dimension loads only on one PCA principal component and one principal component only. And you get this beautiful block structure, which is a good sign if your theory is that personality is a 5-dimensional thing. If we do the same thing for large language models, we get a completely different structure. So for most of the large language models we tested, we don't get a 5-dimensional or 5 PCs at all. One exception would be here Llama 3.1 70B instruct, which has a pretty well 5-dimensional principal component structure here, and which leads to like being able to say, okay, let's look at the next step and look a little bit closer here. And the closer look for psychologists is called confirmatory factor analysis, where we also specify the concrete model of personality, namely the equation that I had in the example, and estimate the parameters. In the Big Five personality test, the kind of state-of-the-art model of personality has 3 subdimensions for each dimension of personality, meaning that we have in total 15 dimensions in this equation, plus for each personality dimension, one general factor that accounts for tendencies that people agree more or less. And yeah, I don't want to get into too much detail, but what we are interested in are these fit metrics, CFI and TII, and the root mean squared error adjusted. The CFI and the TII are basically statistical model fit tests that punish for too many variables and compare the fit of the model to an independent model. And these values should be greater than 0.95. They can be 1 at maximum. And as you can see, even for the human samples, these values are not perfect, or you could even say not sufficient, which is also a reason why psychologists still discuss whether personality is a 5-dimensional thing or a 6-dimensional thing, and if this model of personality is really sufficient. So this is an ongoing research. Now, if we do this analysis and calculate these metrics for large language models, we get even worse scores. Here on the bottom right, you can see that no fit index or error metric is sufficient. And even for Llama 3.1, which looked kind of nice in the PCA, the fit metrics are not sufficient at all. What is kind of interesting is that the reliability scores, which are also often in machine learning papers, they are pretty good, and you would report them as sufficient. That doesn't mean that this is a reliable measurement, but it might mean that it reliably measures the wrong thing. So it is necessary that these fit indices are sufficient, have sufficient fit before we look at the reliability scores. So they can be somewhat misleading. I will skip a little bit through the last finding because of the time, but we also uncovered a significant agree bias for most of the models we tested. So if we score these answers for the true key items with a 5 for strongly agree and 1 for strongly disagree, and for the false key items we just invert this, we can sum these scores up, and then we measure the inconsistency. The blue distribution here is the inconsistency of the humans. So sometimes people say, I am an extrovert, and then they also say, I'm an introvert. And this is somewhat, so they agree to both questions, then they would also have an agree bias. And what we see here is the yellow lines are the agree biases of the models we tested. So some, in our case, GPT 3.5 and Llama 2 70B chat, had even significant agree biases compared to the human distribution. So kind of unhumanly agree biases. Okay, in summary, we can say that human personality inventories do not measure the same thing in LLMs as in humans. That doesn't mean that LLMs don't have personality, but it is most certainly something different. And we also found this agree bias. So in general, if we transfer human tests to large language models, we should always do this measurement invariance investigations before we interpret the results as measurements of personality, intelligence, or whatever human construct. Yeah, we have also a position paper where we talk about this a lot, so feel free to look at that too. Thank you. I would love to answer some questions.
Thanks, Tom. We have time for a quick question. Anyone has any questions? Okay. Well, then I can ask a quick question. What are your thoughts on like higher personality scores for these LLMs being interpreted as the model having human-like traits?
Higher personality what?
Higher personality scores, right, from that box plot that you were showing. If the model has, if the LLMs have like better from all the 5 bounds, what are your thoughts on them being interpreted to be the model having human-like traits?
So in this plot, you mean with Llama 3.1?
Yeah, the third one, I think the Llama 3.1.
Yeah, so I don't think that this has something to do with human likeliness. So basically, or let me say that it has something to do with consistency, I think. So in some sense, if the model is capable of identifying that extraversion questions have something to do with the same thing, then this PCA here will look like that. So if that is human-like, then I would say it has something to do with it. And
Yeah, there's interesting results. Yeah. Oh,
yeah.
thank you. Okay,
Thank
then
you.
we come to the end of this session. Next, we are now at a coffee break, and we resume at 11:15 for the next session. Thank you.